MacMaths, let's do some maths today. Forces. Okay guys, I'm going to just give you an introductory lesson. It was never really explained to me that well, forces, so I'm going to try and do my best. I've been thinking about a way of explaining it to you. Okay, and I'm going to talk about this 10 kilogram block. I'm going to put it in some different places. I'm going to take it out to space. I'm going to stick it on some ice, and we're going to look at how the forces that apply on this 10 kilogram block. And we're also going to look at, I'm going to give examples of a car and a hot air balloon as well. Right, let's get started then. So this 10 kilogram block, okay, it has a mass of 10 kilograms, and there's a force acting on that, and that force is what we call weight. It acts down, and it acts down because the Earth has gravity, and gravity creates everything, is a force that creates everything to accelerate towards it at 9.8 meters per second, per second squared, as we've seen in the last set of lessons. Okay, so if this is accelerating down at 9.8 meters per second squared, if we drop it from up above, then the force acting on it is actually its weight. You sometimes see this written as mg, mass times gravity. 10 times 9.8, it would be 98 newtons acting down. That's the force. But where does this come from? It comes from one of Newton's laws. I think it's his second one, and it's a really simple one, and it's just this: F equals ma. Couldn't be easier. Lovely. I'm glad he came up with such a simple one. The force of any object is equal on any object is equal to its mass times the acceleration. So this has a mass of 10 kilograms. It's accelerating at 9.8 meters per second squared. It creates a force of 98 newtons. Beautiful. Right, so let's have a look at this. So this weight, this force of 98 newtons is causing this to accelerate. It's accelerating at 9.8 meters per second squared. Until, of course, and that's the only force acting on this. There is other forces as it's falling. There is a resistant force. I'll put RES. I'm not just going to put R, you'll see why in a second. There's a resistant force. That resistant force, remember, because it's falling towards our planet, it's falling through this soup of molecules, and those molecules create an air resistance. So there is a resistance that will, a force that will be acting against this 98 newtons, just to slow it down a little bit, so it won't be quite accelerating at this 9.8. It'll have a sort of parachute effect, okay, a small parachute effect. Okay, but we often, when we're doing maths, we just ignore that because the air resistance on most things that appear in our questions is actually quite small. Okay, so let's take our block, and it hits a table. It lands on a table. Okay, so let's do that now. So let's draw our block now. It's been dropped, but now it hits this table. Okay. Well, that force is still there. That weight is still acting down. It's putting strain on the legs of those tables. And it's still 98 newtons because it's mass times the acceleration, which is gravity. So that force is still acting down. But now there's a new force, because that 10 kilogram block is not moving anymore. And if it's not moving, there has got to be a force that's stopping it from moving, because this 98 newtons is pulling it down in that direction. That means that there must be 98 newtons acting in the opposite direction. And that is called a resistant force. It's an equal and opposite reaction created by the strength of this table. It's not less than 98 newtons, because if it was, this would keep on moving and it would crumble, the legs would collapse. And it's not more than 98 newtons, because if it was, then this force would be greater than this force and it would start moving up. as it does in a lift. If someone stands in a lift, the force of the floor is greater than the force of the person or the people in the lift. So this is what we call, this resistant force is called an equal and opposite force. It happens every time we have an object that has a weight, and it's the second force I always write on my force diagram when I'm doing a force diagram for anything I do. After I've put in mg, I always put in, if it's on a surface, this force, this reaction force. Okay, and it's an equal and opposite force. So there we go. This means that our block now is in equilibrium. It's not moving. If this was not a very strong table, then these legs may not be able to take this 98 newtons. Okay, if this was 100 kilograms, that table might collapse and it might keep on moving. But here it is, it's in what we say equilibrium. It's not moving anywhere because the forces all balance out. And we can work out this R because it is in equilibrium. Because it's not moving, of course it has to be 98. Let's take our 10 kilogram force now and let's put it somewhere else. Let's take it, there's our sun, okay, and there's Mercury and Venus and Earth and Jupiter. Let's take it past, you know, all of our planets in our solar system, and let's put our 10 kilogram block out in space outside of our solar system. Our 10 kilogram block now is not being acted on by any gravity of any system, okay, from our sun or whatever, so there's no pull on it whatsoever. So unless we apply a force to it, now that it's out in space, it's got mass, it's still got that 10 kilograms, but it is weightless, okay? So our 10 kilogram block, let's just move it over here. I have to apply a force, of course, to move it over here, and then an equal and opposite force to stop it, okay? So there's our 10 kilogram force, and now it's out in space. It's actually just there, weightless, it's not moving. And if we apply some forces to it, so if I applied a force that way of 5 newtons, pushing it from below, but also push it from the top by 5 newtons, and push it from that side, so I always draw it in the opposite direction, so 3 newtons that way. So in space, I'm going to apply some forces to it, and I'm going to apply these 4 forces. Now you can see what's happening here. 5 newtons I'm pushing it that way is being balanced by the 5 newtons. So it's not got this longitudinal sort of movement, it's staying there. But then the 3 and the 7 don't balance. Okay, I've got 3 newtons acting that way, but I've got 7 newtons acting that way. This 7 newtons cancels out the 3 newtons and creates another 4, doesn't it? Because this is 3 plus 4 newtons. The 3 cancels out that 3, leaving it with 4 newtons. So this is equivalent, all of this now is equivalent to our 10 kilograms with a force of 4 newtons acting in that direction. And that 4 newtons will make our block move in space. Okay, how much it will make it move, well, we can work it out by using Newton's law, because F equals ma is a rule that works across the universe. It's a rule of physics. The laws of physics apply across the universe. There are little pockets where this may not apply, but let's not talk about that now. So we can work out what would happen to this block. Well, because if we apply F equals ma, it's hanging around in space until I come and do this to it. If I apply F equals ma, the force is 4 newtons, its mass is 10 kilograms, and the acceleration. So dividing both sides by 10, we can see that the acceleration, 4/10, is 0.4. It will, relative to someone stood on Earth, it will start to accelerate at 0.4 meters per second squared. In other words, it will increase its velocity by 0.4 meters per second every second. It will start to accelerate, and it will accelerate in that direction. Okay, so there we go. We've broken equilibrium here. We've applied F equals ma, and we've seen that when we have, this is called a net force, by the way. Net meaning, you know, it overcomes other forces. It's the bit that's left. So we've got a net force. And you hear this word net, don't you? In many different situations, your net spend. If you if you get £1,000 a month for your salary, that you've earned £1,000, but your outgoings, all your bills are £600, you've got a net amount of income of £400 to go out and spend and enjoy yourself and buy meals. You can't at the moment because of COVID, but when I get my wage packet, I get my salary, and then all of the tax and national insurance and everything is taken out, and it tells me my net amount. And this is our net, what we call our net force, and that's what is referred to here in the F equals ma. Okay. Let's change something now about our force in space. Okay, it's all very convenient, isn't it, having these forces just acting that way, up or down. But that's not going to be the case in future. Maths is going to get a little bit harder than that. So, a bit more realistic. So let's just say, for instance, I remove two forces. I remove this 5 Newton force here, and I remove the 3 Newton force here. These two forces are still acting on it. So where's it going to move now, and by how much? How can we apply F equals ma now? Well, this is where we apply our rules of vectors. So think about this. So 7 newtons is acting that way, and 5 newtons is acting that way. You can probably see it's going to be going in that direction. As imagine 2 strings pulling it there and there. They're going to be fighting each other, and it's going to be going off in that direction. Well, to find out exactly what direction and by how much it's going to start accelerating, well, we use that triangular law of vectors. 7 newtons that way. Let's just change the way that we write that. That is a 7 Newton force, and also acting on it, but I'm going to slide it over here, is a 5 Newton force. So I've gone 7 newtons that way, 5 newtons that way, and those two combine to create this here. This is our resultant force, not a reaction force here, but a resultant force, sometimes again called R. A resultant force that is acting in that direction. And we can use simple trigonometry and Pythagoras to find out what that force is and in what direction it's acting. Well, first of all, this angle here, let's go with theta. I do like baked beans. Okay, if I go with theta for this, you know from basic trigonometry that the tan of theta is equal to opposite over adjacent. This is a right angle triangle. So the tan of theta is equal to 5/7. And if we inverse tan of 5/7, and I'm doing that now, and my friend told me, Jeff told me, that you can't see the screen because he watches my videos. He's 65 and doesn't know what day it is, so he doesn't understand any of this. He's a PE teacher, that's why. Inverse tan of 5/7, and if we do that, is 35.5 degrees. So this will start moving off at an angle of 35.5 degrees to the horizontal. And we could change it into a bearing if that was north. Okay, but it's going to be, that's the direction it's moving. And you can probably guess that the force is actually those two forces combined, a bit of that and a bit of that. Well, Pythagoras takes that care of that, doesn't it? So the square root of 7 squared plus 5 squared. You know, you've got the two smaller sides, and this is the hypotenuse. And that gives us root 74. So let's just change that, 8.6. So by Pythagoras, it's equivalent to an 8.6 Newton force in that direction. Okay, now we can apply F equals ma. We know that the force is 8.6 newtons. There's our F, and that is equal to ma. In other words, the mass times the acceleration, divide by 10. Okay, and you can see that the acceleration is 0.86 meters per second squared. and that's how much it will start to accelerate off in space. Okay, so we've looked at this concept of net force, and we've applied when it is broken and a force is greater, it's always going to make an object accelerate off. Okay. What we're going to end up doing, of course, is going the opposite way. We're going to get these forces that are acting in all different directions, and we're going to do what we call resolve them, do the reverse of what I've done here to find out, break them down into their horizontal and vertical components, so we can simply do takeaways, top takeaway, bottom, or left takeaway, right, to find out the net sort of forces of those. That's what we're going to end up doing. Now then, let's take our block back to planet Earth, and let's do that now. Let's take our block back to planet Earth and drop it, there he is, on some ice. Now the reason that I've dropped it on ice is because at AS level we don't deal so much with friction. You're told about friction. Frictional force is a force that acts between two surfaces. It resists motion, so it's always there. But obviously in some situations that friction is minimal, so we ignore it, and that's why I've decided to drop this block on ice. You'll see it, you know, people, mathematicians write it like that, an F. I don't like the F because it gets mixed up with this F here. I put a little R there, and I don't even like it at the bottom, although that's where it's acting, isn't it, between the two surfaces. Okay, so I normally, when I do it from the middle of the block. So we'd have frictional force if we were trying to move it in that direction, but this is on ice, so we're going to describe this surface as smooth, and whenever you see that word smooth, it means they're telling you ignore friction. So there's no friction here, and let's apply a force to it. Let's apply a force of I don't know, 5 newtons, and let's apply that force at 40 degrees. So if it was pulling 5 newtons in that direction horizontally, I could just put the 5 in there, couldn't I, and divide it by 10 to get the acceleration. In other words, it would, if 5 newtons was pulling in that direction horizontally, it would accelerate at 0.5 meters per second squared. But I've actually chosen to pull at a string like that, or a rope, 5 newtons, and pull it along at 40 degrees to the horizontal. Okay, now if we wanted to work out how fast it moves now, this 5 newtons is doing 2 things. It is pulling it in that direction, like you would pull a sledge along it, you know, in the snow. So it's pulling it in that direction, but it's also giving it a bit of lift. It's pulling it up a little bit. That, you can see, it creates this sort of vector effect again, this, you know, horizontal and a vertical vector. Now this vertical bit is not affecting the horizontal motion of our block now on the ice. It's giving it a little bit of lift, but this is, remember, this acting down is 98 newtons. That's not enough to, when we work this out, it's not going to be enough to compensate for the 98. It's going to be less than 98 acting up. Okay, what it is going to do, it's going to mean that the resistance force of this block acting on the ice is going to, it doesn't need to be as much, because there's not as much of the 98 newtons acting down. This cancels a little bit of this out, so the reaction force, you know, will be a little bit less. We'll look at that in a second. But it's this one we're interested in, because this one here, the horizontal component of this 5 Newton force acting at 40 degrees, is the one that's going to pull it along. So by trigonometry, we're going to go the reverse of what we did before. This side here, let's call this the X side, because it's the X force, because it's acting in the horizontal direction, the X-axis, and this the Y force. Okay, horizontally, we'll talk about the Y in a minute, that's less important to what we're doing. Horizontally, this force here If you remember, we know I can move my 5 newtons because the hypotenuse there now is 5 newtons. So in our triangle we can see that the cos of 40 degrees is equal to the adjacent over the hypotenuse. So the cos of 40 degrees is equal to x over 5. So 5 cos 40 is the x component of this 5 Newton force. I'll work that out on my calculator. 5 times cos 40. And Jeff, if you're watching, I'm sorry you can't see the screen. Okay, so this is 3.8 newtons. So actually, only if I'm pulling it up at 5 newtons, because I'm not going at the horizontal of 5 newtons, only 3.8 newtons of this is acting in that direction. So that means the acceleration would be, well, 3.8, there's our force, is equal to the mass times acceleration. So dividing both sides by 10, you can see that it would actually start accelerating on the ice at 0.8 meters per second squared. That would be the acceleration of it, because 0.38 times 10 is 3.8 the force. Okay, while we're here, we might as well look at this reaction force now. How is that affected? Well, y, we can work out y by doing the same bit of maths here, can't we? We can say that the sine of 40 degrees is equal to opposite over hypotenuse. So the sine of 40 degrees is equal to y over 5. So 5 sine 40 is equal to y, and we can work that out. 5 sine 40, and that's a 3.2 Newton force acting. So this 5 Newton force will create 3.8 newtons that way and 3.2 newtons up. Okay, so that means that this is still not moving, it's not collapsing through the ice, and it's not starting to float up, because this 5 newtons out there. What's happening is that this reaction force now has reduced. This reaction force now only has to be, and it must be, 98 take away 3.2 is 94.8 newtons. So it's not moving up or down. That means 98 newtons is acting down because that's the weight, but 3.2 newtons is acting up. That's the lift part of this force, and the reaction force now is only 94.8 newtons to counteract the 98 newtons acting down, because those two added together have to be equal to that. Okay, so the reaction force is less. Okay, so that's more of what we're doing. You're going to get into the habit of resolving forces, and they're not always going to be conveniently horizontally and vertically, and there's going to be situations where you get multiple forces and angles, so you have to resolve this force that way, and then you can start, once you've done that, you can see which bits overtake each other, so you know whether it's moving left or right and so on. Okay, let's have a look at a slightly different situation. I want to explain, and this is what I just used to when I was young, struggle to get my head around, that if we apply a force, a net force to something, and it is a net force, it's always going to accelerate. What happens when we reach a point where we stop applying a net force? Well, think about a car, and of course that's why I got confused, because it's not really a force, it's a net force. Think about a car. When you are in a car and you hit the accelerator, your engine creates a force, quite a powerful force of many thousand newtons, and your car starts to accelerate. You may reach 60 miles per hour. Okay, so let's say you reach 60 miles per hour, 60 mph. Okay, so you're reaching 60 miles per hour. You've accelerated up to that point, but at that point you don't want to travel any faster than 60 miles per hour because there's a sign. It's in a circle. It's telling you can't go faster than that and you don't want to get into trouble. So what do? If you take your foot off the accelerator, in other words, stop this force, the engine, okay, is going to stop working. Your car is going to start to slow down. You'll notice that your car will slow down immediately. And that's because there are other forces acting on this car. There's actually, we cannot ignore air resistance now of a car because it's too big an object. So there is air resistance that will be acting on that. There will also be friction, in the wheels. There'll be quite a lot of frictional force acting in the car, on the wheels, on the surface and so on. So there's quite a lot of forces acting against the car. If the car was on a slight slope as well, there it is, sorry about my drawing, that car looks like it's collapsed and it's moving up in that direction, you've got your resistance force, your air resistance force, you've got your frictional force, you've got your resistance force there, and this mg acting down, the weight of the force on the road, well, again, we're going to have to resolve that because that is a downward force, but it's also, well, it's acting down like that, isn't it, towards the planet. This is on a slope, but that gives you a downward force on the road, but it also, to create our triangle, acts down that way. If you stopped at all forces, it would start to roll down the hill, wouldn't it? So again, using that, working out that angle, we can work out, it creates a force, some fraction of mg, acting, there's our mg there, but some fraction of that is going to be acting down the slope. So there's all sorts of forces that are acting against our engine of our car, particularly when it's on a slope. That just adds another one. So that means that when we accelerate up and take our foot off the accelerator, if you want to carry on travelling at 60 miles per hour, you still have to have your foot on the accelerator. You still have to apply a force to your engine. And that force, if you have constant velocity to keep it at 60 miles per hour, that force has got to exactly match the resistant forces to your car. So there is in effect no net force. This force matches these two. You've got your foot on the accelerator, it's travelling at 60 miles per hour. There's no net force because that is equal to that. That means it will stay at 60 miles per hour that you've accelerated up to. We're not going to apply this because there is no net force now. It's not this force, it's the net force. It's that take away that, and that take away that is 0. So there's no acceleration. Okay. So just have a think about that. That force is the net force. You can be moving at a constant velocity, and it's just like our block in space. Unless you apply a force in another direction, it's just going to carry on, on its own without accelerating or slowing down. A unique situation you sometimes get is a hot air balloon. You sometimes get questions like this, a hot air balloon. Because a hot air balloon is a bit of a unique situation. A hot air balloon, it has the weight of the basket and the people in it. Let's draw someone in it. There we go. There's me in it. The weight of the basket and the people in it, and actually the balloon itself, has a mass times gravity. But by applying the heater and making this air lighter inside, we create a force. We create a force that's greater with this warm air expands and rises. This creates a force of our helium that takes our basket up, and we reach an altitude where they let it cool down sufficiently inside, don't apply any more flames to it for a bit, and it just stays hovering above the ground. The ground is down here. In other words, we reach a point where mg is equal to the force acting up. That's that force that the helium is acting in there, trying to escape the outer atmosphere. If this was too much, if this was too light, we'd never stop it and we'd drift off to the edge of our atmosphere, and it'd be, obviously we'd lose our lives then. So there's got to be some careful design. Also, what happens is that wind catches our air balloon and starts to move it along here, but it reaches a point, or in altitude, or where often air balloons do, where it doesn't keep then accelerating. You get the air resistant forces, and obviously there's going to be a lot of those hitting, and when those two balance, that's when you often get, when you see a balloon, it's not accelerating, it's just drifting across. This is cancelling out the weight of the balloon at this particular point, and the air resistance is matching the force that speeded it up originally, and it's just drifting along at constant velocity. And you often get these questions that start with an air balloon that has a constant velocity in a particular direction of, I don't know, 10 meters. Oh no, that's a bit fast. That 2 meters per second. Okay, and that's its constant velocity, and that is exactly the same as just a block in space that isn't moving. It's there's no extra net forces on it. There's no extra net forces on our 10 kilogram block when it was just hovering outside of the solar system. It's the same maths applies to that, and the only way that this is going to change the situation, it's like it's in equilibrium. It's the same, even though it's got a velocity, it's like it's in equilibrium. The only way it's going to change, if one of these forces increases, then it's going to start accelerating up, down, left or right. Or if two of these change, it's going to start heading down in this direction. Okay, perhaps if this gets more than that and the air resistance starts to drop off, or the wind resistance increases, so you get more of a net effect this way. Okay, so it's not just about something being in equilibrium is still, it can be in equilibrium and moving with constant velocity, is what I'm trying to say to you. That car where the engine force is matching the resistant forces, so it's going at constant velocity. That is the same, it's classed in physics as the same as something being in equilibrium. You can have a go now at exercise 10A. It's getting you to work out or just draw little force diagrams. It's the very silly and simple ones, just an apple falling from a tree. What force is happening to that apple? Well, the only force, it's just asking you to draw force diagrams. The only force acting on that apple is mg, because it's getting you to ignore air resistance. So it's just going to accelerate down at 9.8, but the force is going to be whatever weight of that is. It might be 0.1 kilograms or something like that, 100 grams apple. So 0.1 times gravity times 9.8 would be the force, the weight of it acting down. There's another one, it's got a trapeze, ropes of equal length, maybe somebody hanging from it, there's a person, there's their arms. Okay, well, that person and the weight of this trapeze, if they say this has a mass as well, doesn't it, and the weight of this, well, that looks, sorry, a bit rude, but all of this has an mg, working down the weight of the bar and the person all together, and if they're not moving down because it's just hanging there still, that means that the tension in these two strings here, tension 1 and tension 2, must be matching. These are the three forces, the two tensions in the strings and the mg of the person and the trapeze. They're the forces that are acting here, and obviously that if they're not moving, if it's just hanging there sort of still, then this force here is equal to these two added together, isn't it? They've got to be equal. There's no net force. It's not accelerating up or accelerating down. If it's all symmetrical, if these strings are the same length and the same material, then the tensions will be the same. So if this is, I don't know, I'm just making numbers up now, 500 newtons acting down, that's the weight of all of this, then these two tensions are going to be 250 newtons each, aren't they? Acting up. And if they were more than that, then this would be moving up like a lift. If they were less than that, then this would be, you know, bungeeing down, and so on. I just glancing up, because I do have the book in front of me, you know, you get very simple questions that are telling you the situation is in equilibrium, and they've kept it nice and simple. Everything is horizontal and vertical. I'm not going to do this question, but I can see they've got this block, and they're saying there's this force here which is Q plus 10 newtons, and there's another force of 3p newtons acting down. Okay, so this, yeah, and 3p newtons acting down, and then there's a force of, what they're saying, oh, now they've got 5q newtons, they're like the q's and the p's, and p newtons acting that way, and 50 newtons acting that way. Okay, so a diagram, they're telling you it's in equilibrium, and they're asking you to work out the values of p and q. Well, if it's in equilibrium, it's not moving anywhere, so that equals that. That has to be. So you can see straight away that p is equal to 50 newtons. Okay, if p was more than 50 newtons, it would be moving it. It wouldn't be in equilibrium. If it was less than 50 newtons, it would be moving that way. And q, you can see that 5q up has got, it's not moving up or down, so the 5q up has got to be equal to q plus 10 plus the 3p force acting down. And you can see we've already worked out p from that, so it's not even simultaneous equations so much. It's even, well, it is simultaneous equations, but it's very simple, isn't it? So 3p is 150, we know that because we know what p is, newtons. I'm not putting my units on. So now we've got that, haven't we? Okay, and we can add 10 to that one that takes, so we can see that 4q, careful how you say that, is equal to, take q off both sides, 160, and q is 40 newtons. So we've worked out p and q. I said I wasn't going to work it out, I couldn't resist it. I do love mechanics. Okay, it's beautiful. It's all horizontal and vertical at the moment. Okay, but I'm going to go through particular questions with you. So I'm going to go through, not today, this is the end of the lesson now, but I'm going to look at splitting those resolving forces, and then I'm going to look at all the situations that you would get on an exam in terms of cars pulling caravans, pulleys, and so on. Okay, hope that all made sense.